Greetings. So let's talk about a situation where we have vector spaces and we have a basis for each vector space. So for vector space U, the basis would be B. For vector space V, the basis would be C. For W, it would be D. So these are bases, and these are bases, and these are the vector spaces for which we have the basis. So these are the names we have for them. Let's also have these linear maps from V to U, and then from U to V, and also linear map G that basically goes from U to V, and from G goes from V to W. And then we have GF as a composition goes from U directly to W. So if we multiply the G and F into GF, and we then have that if U, V, and W, granted that they are finitely generated, all right, and they have the basis as stated, then matrix of GF, this composed linear map, in respect to basis BD, should actually be equal to G in respect to CD times F in respect to BC. And so let's do the proof for this statement. Well, it's quite straightforward. All we need is just to expand directly. We know that for any x, using another theorem, we know that for any x it applies that GF of x, this whole thing, in respect to D, should actually be equal to this matrix of G in respect to C and D times the image of x under the default F in respect to C. But this stuff directly translates to also G in respect to CD, but the f of x in respect to C part can be written as matrix of F in respect to BC times x in respect to B. We have a parentheses here, but this thing we can just reorganize the parentheses and just rewrite it as G in respect to CD times F in respect to BC, this whole thing in a parentheses, and all that x in respect to B here, which is exactly what we wanted to show. So we directly go there because this was the goal here.